Electrons. We often think of them as just carriers of electric charge, little couriers delivering energy. But electrons hold a secret, a deeper property. It's called spin. This spin makes each electron behave like a tiny, incredibly small magnet. Spintronics is the exciting field of science dedicated to understanding and using this electron spin. It's a whole new way to think about building electronic devices. We are not just using the electron's charge anymore, we are tapping into its intrinsic magnetism. This opens up a universe of possibilities for the future of our technology. Imagine devices that work in ways we've only dreamed of, all thanks to this quantum dance. So what exactly is a spin current? It's a flow, a movement of this spin property. Picture a river, but instead of water molecules flowing, it's the spin direction that propagates. The electrons themselves might not all be marching in a single direction, like in a traditional electric current. Instead, their tiny internal compasses, their spins, can be aligned, and this alignment can move. This is fundamentally different from the charge current that powers our homes. A charge current is about the bulk movement of charged particles. A spin current is about the flow of spin angular momentum. This is a subtle yet profoundly powerful distinction found in the quantum realm. Let's compare this to a charge current. An electric current, as we commonly know it, is fairly straightforward. Electrons, with their negative charge, are pushed through a material, like water through a pipe. They flow through wires, creating the electricity that powers our world. A spin current, however, operates on a more nuanced level. Electrons can possess a spin that's up or down, a quantum mechanical property. A spin current means there's a net flow of one spin type. For example, more up spins moving in one direction than down spins. It's even possible for spin to flow without a net flow of charge and vice versa. It's a fascinating interplay of fundamental properties. Every single electron in the universe possesses this spin. It's an intrinsic property, as fundamental as its electric charge or its mass. It's not that the electron is physically spinning like a tiny ball. That's just a helpful classical analogy for a purely quantum mechanical phenomenon. This inherent angular momentum makes each electron a miniature magnet. When we, as scientists and engineers, learn to precisely control and manipulate this spin, we unlock incredible new capabilities. We can begin to design and build devices that are significantly smaller, operate much faster, and consume far less precious energy. The universe has gifted us this tool. We are now just learning its language. We have these minuscule magnets, the spins of electrons. The next grand question is, how can we control them? How do we make these tiny compass needles point in the direction we desire? This control is absolutely crucial if we want to build new kinds of devices. If we can reliably flip these tiny electron magnets from one orientation to another, we can store information. We can represent the ones and zeros that form the bedrock of our digital world. This is the very heart of digital technology. But now, instead of solely relying on the presence or absence of charge, we are using the orientation of spin. This refined control allows us to manipulate magnetic states with unprecedented precision. One clever method to control these spins is known as spin transfer torque. You can call it STT for short. Imagine a fast-flowing stream of water turning a water wheel. The moving water transfers its momentum to the wheel, causing it to rotate. STT operates on a similar principle, but at the quantum scale. A current composed of spin-polarized electrons whose spins are mostly aligned in one direction, is made to flow into a magnetic material layer. These incoming electrons then transfer their spin angular momentum to the magnetic moments within that layer. This transfer can exert a torque, a precise twisting force, on the layer's overall magnetization. This induced torque can be sufficiently powerful. It can be strong enough to completely flip the magnetic orientation of the material it acts upon. If the magnetic layer was initially pointing, say, north, the application of STT can cause it to flip and point south. This is precisely how we can write digital data using spin. North could represent a binary 1, while south could represent a binary 0, or vice versa. This very mechanism is employed in an advanced type of computer memory called MRAM. That stands for Magnetic Random Access Memory. It's known for being very fast and, importantly, non-volatile, meaning it retains data even when the power is turned off. MRAM that utilizes STT is not just a theoretical concept, it's already a commercial reality. It offers us a tantalizing glimpse into the future of computer memory systems. These sophisticated MRAM devices typically feature a component called a magnetic tunnel junction. This junction consists of two distinct magnetic layers, separated by a very thin insulating barrier. One of these magnetic layers has a fixed, unchanging magnetic orientation. It serves as a reference. The other layer, the free layer, can have its magnetization flipped. By carefully passing a spin-polarized current through this junction, we engage STT. We use it to flip the free layer, thereby storing a bit of data. This technology promises higher storage density and lower power consumption compared to many conventional RAM types. STT is indeed a powerful tool in the spintronics arsenal. However, the relentless spirit of scientific inquiry means researchers are always seeking even better, more efficient methods. This quest has led to the development of spin-orbit torque, or SOT. This is another sophisticated technique for controlling those tiny electron magnets. SOT relies on a truly fascinating and subtle quantum mechanical effect. This effect can arise from phenomena like the spin Hall effect or the Rashba effect. These effects typically manifest in certain types of materials, particularly heavy metals like platinum or tantalum, or at the interfaces between different materials. They are a beautiful testament to the intricate and often counterintuitive laws that govern the subatomic world. So how does spin-orbit torque actually work its wonders? When an ordinary electric charge current flows through one of these special SOT-active materials, something remarkable happens. Due to strong spin-orbit coupling within the material, electrons with upspin tend to get deflected in one direction, perpendicular to the charge current. Conversely, electrons with downspin get deflected in the opposite direction. This separation of spins creates a pure spin current. This newly generated spin current then flows into an adjacent magnetic layer, and much like with STT, this spin current exerts a torque on the magnetization of that layer. It can be used to switch the magnetic state efficiently. Notably, the charge current doesn't need to flow directly through the magnetic bit itself. SOT presents several compelling advantages when compared to STT. One significant benefit is that the electrical paths used for reading data and writing data can be physically separate. This separation can lead to devices that are more durable, as the delicate magnetic storage element experiences less stress during write operations. It can also contribute to faster device operation and potentially greater energy efficiency in certain device architectures. This is partly because the charge current, which can generate unwanted heat, does not need to pass directly through the sensitive magnetic tunnel junction during the writing process. This decoupling offers engineers far greater design flexibility for spintronic components. Furthermore, spin currents can achieve more than just flipping the direction of magnets. They also provide a way to control a property known as magnetization damping. You can think of damping as a kind of friction that affects magnetic orientations. It's what causes a disturbed magnetization to eventually settle down and stop precessing. Sometimes we want to reduce this damping, allowing the magnetization to respond more easily and quickly to external stimuli. Other times we might want to increase damping for greater stability of the stored magnetic state. Spin currents, when injected into a magnetic material, can effectively tune this damping. By precisely injecting spins, we can either counteract or enhance the natural damping processes, giving us another valuable knob for controlling magnetic behavior. To bring all this spintronic magic into the real world, we require specialized materials. We need materials that are exceptionally good at generating these spin currents. Or, we need materials whose inherent spin states are particularly easy to manipulate and control. Heavy metals such as platinum, tantalum, and tungsten have proven to be excellent candidates for generating spin currents via SOT, thanks to their strong intrinsic spin-orbit coupling. Another incredibly exciting class of materials being explored are topological insulators. These exotic materials possess the unique property of conducting electricity only on their surfaces. And on these surfaces, an electron's spin is often locked to its direction of motion. Scientists are constantly discovering and meticulously engineering new materials that exhibit novel and enhanced spin properties. We've already touched upon MRAM and how spin currents are making it faster and more efficient, but the potential applications of spintronics extend far beyond just memory. Imagine logic devices, the fundamental building blocks of computer processors, that operate based on electron spin rather than just charge. Spin-based transistors could be vastly more energy efficient than their conventional counterparts. They might even enable new forms of computation that current transistors simply cannot perform. Think of neuromorphic computing, which aims to mimic the structure and efficiency of the human brain. Or envision devices that can seamlessly perform both memory storage and logical operations within the same structure. Spin currents are steadily paving the way for these beyond CMOS technologies. Why is there such immense excitement and research focus surrounding spin currents? There are two overwhelmingly compelling reasons: significantly improved energy efficiency and remarkable operational speed. Flipping the state of tiny magnets using spin torque can require substantially less energy compared to traditional methods that rely on generating magnetic fields with electric currents. This advantage becomes particularly pronounced at the very small scales of modern nanoelectronics. Furthermore, these spin-based switches can operate at incredible speeds, potentially reaching picosecond timescales. A picosecond is a mere trillionth of a second. This translates to computers that run much cooler, reducing energy waste, and perform complex calculations at absolutely breathtaking speeds. Our increasingly digital world deeply craves such advancements. In essence, spin currents are far more than just an interesting scientific curiosity. They represent a truly fundamental shift in how we approach and design electronics. We are steadily moving beyond the paradigm of simply pushing electric charge around in circuits. We are now learning to harness a deeper, more subtle quantum property of matter: the intrinsic spin of the electron. This endeavor opens up a vast and fertile new playground for technological innovation. From ultra-fast, low-power computers and high-density memory, to entirely new classes of sensors and quantum information processors. Spintronics, propelled by the remarkable capabilities of spin currents, is undeniably poised to revolutionize technology as we know it. The cosmos has given us these tiny spinning dancers, and we are finally learning their intricate choreography. The future of electronics is quite literally spinning.